In this video, we're going to discuss another business application that involves using binary decision variables. We're going to see how we can model fixed cost in production planning problems. So in a lot of applications, in production planning examples, in production and planning problems, the cost of production usually has two components: a setup cost, that is a fixed cost, and a variable cost that directly depends on the quantity of production, right? So imagine a production line or assembly line. The time that you have to spend to set up the assembly line or production line, that doesn't depend on how many units you're going to produce, 1 unit or 1,000 units. So people are working, machines are idle during that time, during that setup time, and you're paying some cost for that, right? So you're paying some labor costs for just setting up the machines. There's nothing produced during that time, but that is necessary. That setup cost is necessary for actually starting the production. But then that setup cost doesn't depend on whether you're going to produce 1 unit or 1,000 unit or 1 million unit. You have to set it up one time, right? So you have to incur that fixed cost that doesn't depend on the quantity one time. After you set it up, there's going to be variable cost, which is going to be directly related to the quantity. So there's going to be a per unit cost that you have to incur. All right. So so far in the examples that we have worked on, we either considered a continuous type of problem, a continuous type of decision variables, or a binary type of decision variables. Imagine a portfolio selection. In a portfolio selection, in the portfolio optimization problem that we worked on in chapter 11, we assumed that the decisions are continuous. We were only interested in knowing the amount of investment. But in general, when we are making a decision about a investment or a production of a product, we're actually making two decisions. We first decide whether or not we're going to produce that product, whether or not we're going to invest in that alternative. And then if yes, how much we're going to produce, how many units we're going to produce, how much money we're going to invest in that alternative, right? So there are actually two decisions: whether or not, and then how much. If yes, how much are we going to produce or are we going to invest, right? So far, we were only working with one of those decisions. In capital budgeting examples that we solved, the amount was fixed, the amount of investment was fixed. We were only worried about whether or not type of decisions, whether or not we're going to invest, 0 or 1. Whereas in portfolio optimization problem, we didn't care about whether or not type of decision. We were only looking at our objectives, our costs or our revenue only depended on the amount of investment, amount of production. Whereas in this case now, in the fixed cost problem, we are actually considering to formulate both of these cases. And the setup cost here only depends on the decision regarding starting the investment or starting the production. Doesn't depend on the amount of investment. In the variable cost, we care about, for formulating the variable cost, we care about the actual amount of production, all right? So now, because of that, in this specific example, this is going to be a mixed integer. So we will have a production quantity to decide about, which is a continuous type of decision variable. Second, we have a binary type, whether or not we're going to produce a certain product, all right? So this is going to be a mixed where we have a binary variables as well as a continuous variable, right? So we're going to start with a production planning, a very simple production planning with 3 products. And we're going to only be working with the variable cost. Then we're going to add the fixed cost and see how the formulation is going to change. So this is going to be only the variable cost, similar to the type of problems that we have seen in chapter 11, simple linear programming problem. So imagine a production company, RMC, that is is actually producing 3 products, 3 final products: fuel additive, solvent base, or and a carpet cleaning fluid. So 3 final products, and they're using 3 raw materials for producing these final products. The decisions that they're considering to make are the amount of, or the number of tons of each product that they're gonna produce. F, S, and C. F for fuel additive, S for solvent base, and C for carpet cleaning fluid. So this is the continuous type of decision variables, the amount of production. Next, if we know that it's gonna cost, so here we have the list of parameters. All the coefficients are provided in the note here. So for the we have the profit contributions per unit of product, or per ton of each final product. Let's say $40 per ton of fuel additive. So 40 times F plus 30 times S plus $50 profit per ton of carpet cleaning fluid. So that is the objective function, the profit contribution, total profit contribution. We want to maximize it, subject to the constraints regarding each material. For each material, we know exactly how much of each final product needs, how much of each material is needed by 1 ton of each final product. We know that information. For example, for material one is going to be used in all the 3 products. So for each ton of fuel additive, we need 0.4 ton of material 1. For each ton of solvent base, we need 0.5 ton of material 1. And then for each ton of carpet cleaning, we need 0.6 ton of material 1. So if we just add those together, we have to multiply those by the amount of production of each product. So per ton of fuel additive, we needed 0.4 ton of material 1. So now when I multiply 0.4 by F, it's going to give me the total amount of material 1 that I need for production of F ton of fuel additive, plus 0.5 times S plus 0.6 times C. So that is the total amount of material 1 that I need, that I'm going to be needing for production of F, S, and C tons of fuel additive, solvent base, and cleaning, carpet cleaning fluid, right? And that has to be less than or equal to 20, which is the maximum availability for material 1. So if I follow the same logic and write down the constraints for material 2 and 3, I will have all the constraints, the material requirement constraints, or material availability constraints, and I have my objective function, and I will have my formulation. All right, so I have everything. Now, if I solve it using Excel, I will have my decision variables. with optimal decision variables with the optimal value of profit contribution. But what if I have a setup cost? I did not consider a setup cost so far. Let's say I have a setup cost of $200 per each ton of, I mean, it's not per ton. So setup cost is a fixed cost, is a one-time type of cost that you have to pay if your F is positive. If the the amount of production of fuel additive is positive, you have to incur this cost. You have to pay this cost. And then, so $200 setup cost for fuel additive, 50 for solvent base, 400 for carpet cleaning fluid. And then we have a maximum production of 50, 25, and 40. So we have also this is another additional set of constraints. And if we want to add this setup cost to our formulation, to our previous formulation here, I can't multiply that $200 for fuel additive by F, because this is a one-time cost. I either have to pay this or not, right? It's going to be either 0 or 1. And it's going to be 1, I mean, it's going to be 200 only if F is strictly positive, meaning that I'm producing at least a little bit of F, all right? So in order to be able to add these setup costs to the formulation, we have to define binary variables that are going to capture the decision about if actually production or not, the binary type of decision, whether or not we're going to be producing for each product. So SF, SS, and SC, they're going to be 1 if the corresponding product is produced, and 0 if not. So this is, now we have three additional binary variables added to our formulation. So now if we add those, that's easy now. I can simply add them actually to my objective function. So objective function is going to be the profit contribution per ton multiplied by the tons of production of each product minus fixed cost of fuel additive, fixed cost times whether we are going to produce that product, minus 50 times whether we're going to produce the solvent base, minus 400 times whether we're going to produce the carpet cleaning fluid, right? So, and then the material requirements are going to be the same. Material requirements only depends on the quantity of production. So this is important to note that. But then we have to add another one. So this is very, very crucial. So if we have this condition, guys, if F is positive, strictly positive, I want SF to be equal to 1. All right. So I want this is the logical connection between SF and F. And I have to have the same thing for S and SS and for C and SC. All right. So let me just write them down. So this is a logical constraint that has to hold true. If C is greater than 0, meaning that I'm producing something of, I'm actually producing, doesn't matter how much. If that is the case, then I'm investing. I'm actually producing carpet cleaning fluid. If that is the case, then I have to, then SC has to be 1, and this has to be deducted from my profit function. But if S is 0, sorry, but if C is 0, SC should be 0, and I should not incur this cost. So this should not be deducted, all right? So this set of constraints, if F is the continuous variable, is positive, the binary variable regarding that, regarding the same product, has to be 1. And this is how I capture that. The continuous variable less than or equal to a large number, which in this case is the maximum fuel additive that I can produce, times the binary variable. All right, so continuous variable less than or equal to, this actually is continuous variable time, continuous variable has to be less than or equal to a large number times SF. Now, if SF is 0, this is going to be 0, F less than or equal to 0, and we know that F is going to be greater than or equal to 0 because of the non-negativity constraint. So that'll force F to be 0. All right, if SF is 0, F is forced to be 0. If SS is 0, S is forced to be 0. If SC is 0, C is forced to be 0. But if SF is 1, F can be any value from 0 to 50. So that's the way that we can connect. These are actually connection constraints, connecting the binary variable with the continuous variable. So now I'm going to go ahead and go to Excel and solve this problem. So we already have the formulation. I just have here the list of all the parameters. We already know the constraint. The only thing that I have to add here, max production, which was 50, 25, and 40 for different products. 50 for fuel additive, 25 for solvent base, and 40 for carpet cleaning. So now I'm gonna go ahead and write down my, we already saw the formulation. So I'm gonna go ahead and only create the spreadsheet model. So the decision variables, there are two types of decisions to be made here. So regarding our final product, the first decision to be made is to produce or not, So that's one decision that we have to make for each one of our final products. The second decision that has to be made, if these are 1, then how much? How much to produce? All right. So regarding each final product, we're making 2 decisions. First, whether or not to produce, how much to produce. If yes. So this, if yes, I said if this is yes, if this takes 1, then this can take a positive value. If this is 0, this has to be 0, right? And that last set of constraints, the connection set of constraints, will make sure that we have this set up, all right? And I'm gonna just do that. So the objective function, is maximization of the profit, total profit, and the total profit is going to be the sum product of the amount of production by the profit contribution. So this would give us the gross profit contribution. So 40 times the amount of production of fuel additive, 30 times the amount of production of solvent base, plus 50 times the amount of production of carpet cleaning. But there is going to be a fixed cost or setup cost as well that I have to subtract from my profit function. So sum product of the fixed cost, and I incur those fixed costs only if I produce. So if this is one, if I produce in fuel additive, I have to deduct $200 from my profit function. If solvent base is 1, I have to deduct 50. If carpet cleaning is 1, the production of carpet cleaning, the decision regarding that, I have to deduct $400. All right. So this is how I write my objective function. For the set of constraints, I have a typical material constraint. So I'm just gonna write them down. So decision variables, objective function, and then the constraints. So constraints for the availability of each material. These are per unit of, per ton of each final product. So material 1, I'm gonna need 0.4 unit or ton of material 1 per unit of fuel additive. So if I just multiply this by the amount of production of fuel additive, it's going to give me the total amount of material 1 that I need for production of fuel additive, plus 0.5 times the amount of production of solvent base, plus 0.6 times the amount of production of carpet cleaning, or I can simply use sum product of the requirements of material 1 per ton of each final product. And I can, since I'm gonna copy my formula, I'm gonna fix these production amount, and I'm gonna so the amount of production, the amount of material 1 that I need has to be less than or equal to 20. And I'm gonna just paste, I'm gonna drag it down. I'm gonna copy paste the formula. So for the third material, the sum product of the requirement of material 3 by the amount of production of product, that has to be less than or equal to 21 ton of material 3. Now I need to write down the connecting constraints, which connect actually connects these two. Every time that you have a mixed binary integer linear programming, you have to connect these two, because I said as soon as this takes a positive value, as soon as the amount of production becomes positive, the binary decision has to be 1. It means that you're producing it. If this is 0, if you decide not to produce, then the amount of production has to be 0. Because of that, we have this logical relationship between these two variables, right? So in order to model that, this is how you model. So if X is your So general connection constraint format. So the general format, let me just, general format of connecting constraints or connection constraint between these two, between a binary and corresponding continuous variable is as follows. So the binary variable, sorry, the continuous variable has to be less than or equal to binary variable multiplied by a large number. So this is what you should remember. A continuous, the continuous variable should be less than or equal to the binary variable times a large number. And in this case, luckily we have the large number. The largest number that the continuous variable can take is 50. So we have that. So we don't need to put, let's say, 1,000,000, even though that's not incorrect. We can still do that. But luckily, since we have the largest value that are large number for continuous variable, since we do have that, the largest, the maximum production amount, we can use, we can actually customize this large number and use 50, 25, and 40 for each one of those. So connecting constraints for the first one, the left-hand side is the continuous variable. That has to be less than or equal to the binary variable times the largest number that the continuous variable can take. How much the amount of production can take? The largest number is, in this case is given to us, is 50. So that's great. And if you do that, you don't have to write X. You don't have to say the amount of production has to be 50 because you already captured that as well. So that is gonna make us not to need that one. But in general, you can put a large number, let's say 1 million, but you still have to write down X1, or the amount of production of fuel additive has to be less than or equal to 50. But if you do it this way, if you replace this large number by the maximum production, you don't need to do that. So that is good. That is perfect right now. And then if you just pick it, if you just drag it to the right, you will have connecting constraints for all your products. All right. So let me check the carpet cleaning. The amount of production of carpet cleaning has to be less than or equal to the maximum production of carpet, maximum allowed production of carpet cleaning times the binary variable. So that's perfect. So we have this is important when we have a mixed binary integer linear programming, and when we are considering a binary and a continuous variable regarding one decision, regarding one alternative, we have to make sure that these are logically connected. And this is how we ensure that by making sure that the continuous variable is less than or equal to the binary variable multiplied by a large number. And if we know the largest number that the continuous variable can take, that's perfect. We can just replace that by that number, and we don't need to. I mean, logically, you can say that. I'm not gonna do that, but just to show you, you can say the amount of production of, this was called F, right? F, I can say F should be less than or equal to 50, and also F should be less than or equal to SF, whether or not we produce at fuel additive multiplied by a large number, 1 million, for example, or 10 million, right? So these two, technically speaking, are equivalent to what we just had, which was less than or equal to 50 times SF, or SF times 50. So this is equivalent. I mean, at the end, the results are going to be the same by implementing this versus these two. All right. So this is the connecting constraint, and this one will make sure that you don't produce more than your maximum production. Or you can replace these two by this one, which we just did that, F less than or equal to 50 times SF. Anyway, so this is how we formulate the mixed integer problem. Let me just go ahead and solve it. So in our solver, we want to maximize the profit, maximize profit by changing the 6 decision variables subject to, I have the material constraints, the left-hand sides less than or equal to the right-hand sides. And also I have 3 connecting constraints, the left-hand sides less than or equal to the right-hand sides. Okay, solving method, simplex LP. There's one last thing before we solve it. We have to make sure that the first 3 decision variables are defined as binary decision variables. So I'm going to add another constraint, only these 3, whether or not, to be defined as binary decision variables. Okay. I think we're all set. Maximization of objective function by changing the 6 decision variables. 3 of them in row 11 are binary. And then I have the material requirement constraints, and we have the connection constraint, which connects the binary and continuous variables. So when I go ahead and solve this, again, I'm not getting any sensitivity report because I have integer constraints, integer variables in my model. But luckily, Excel found a feasible, optimal solution, and all the constraints and optimal conditions are satisfied. So, okay. So let's take a look at the answer here. This is 0, guys. So a number between 1 and 10 multiplied by E minus a huge number, a large number, that is actually 0 in Excel. So you can simply type 0, right? So now that was a very, very, very tiny number, very small number. So actually 0 is, it was supposed to be 0 anyway. So so this is the optimal solution, guys. We are producing only 2 of our final products. And this is how much we produce. For fuel additive, we make the production and we produce 25 units, 25 tons. For solvent base, yes, we produce and we produce 20 tons. For carpet cleaning, we don't produce, and the amount of production as a result is going to be 0. As you can see here, we're not reaching to the maximum production allowed for any of those 3. You see, we're producing 20, 25. They're way less than. We still have some slack here. And for material requirement, we are using up material 1 and material 3. They're binding. Both of them are actually satisfied at equality. So they're both binding. Material 2 is not binding. We still have some slack on material 2. So this is, and then the maximum profit that we get is $1,350. So we are actually, remember, we are deducting only the 250, right? And we don't incur the 400 costs. And that's probably the reason we're not investing, we're not producing carpet cleaning, because of its huge fixed cost.